This presentation provides an overview of how many of today's aircraft produce and utilize AC power. An electrical system is an integral and essential component of all but the most simplistic of aircraft designs. The electrical system for aircraft at both ends of the complexity spectrum share many of the same basic components. Alternating current generators supply the electrical energy for operating aircraft avionics equipment. A generator is a machine that converts mechanical energy into electrical energy by electromagnetic induction. Most modern naval aircraft utilize brushless generators for voltage generation. The brushless generator is a Salient 8-pole, 6,000 RPM AC generator. It has a 12-pole AC exciter and a 3-phase half-wave diode rectifier rotating with the exciter armature and main generator field assembly. More sophisticated electrical systems are multiple voltage systems using a combination of AC and DC buses to power various aircraft components. Primary power generation is normally AC with one or more transformer rectifier units, providing conversion to DC voltage to power the DC buses. Secondary AC generation from an APU is usually provided for use on the ground when engines are not running and for airborne use in the event of component failure. Hydraulic motors, or ram air turbines, may also be incorporated into this system to provide redundancy in the event of multiple failures. Essential AC and DC components are wired to specific buses, and special provisions are made to provide power to these buses under almost all failure situations. In the event that all AC power generation is lost, a static inverter is included in the system so the essential AC bus can be powered from the aircraft battery. Modern naval aircraft use the 3-phase 120-208-volt 400 Hz AC power system in order to meet increasing aircraft power requirements. The number of magnetic poles and rotor revolutions per minute determines the voltage frequency of the generator. Constant frequency requires constant rotor RPM when the number of poles are a fixed quantity. The AC generator rotating field has 12 poles, with adjacent poles being of opposite polarity. Each pair of poles produces 1 cycle per revolution. Therefore, each revolution produces 6 cycles. The output frequency of the generator varies in direction proportion to the engine drive speed. A generator operating at 6,000 RPM is operating at 100 revolutions per second, or at 600 Hz. Constant speed drives are used to drive the AC generators. To produce the proper voltage at a constant AC frequency, a generator needs to spin at a constant specific speed. Since the jet engine gearbox speed varies from idle to full power, this creates the need for a constant speed drive. The CSD takes the variable speed output of the accessory drive gearbox and hydromechanically produces a constant output RPM. Systems of like priority are on a common line called a bus. An aircraft has a group of buses identified by the priority of the equipment it powers. For example, a flight essential bus may power flight and engine instruments. Less critical equipment receives power from an essential bus. Normal systems like mission equipment may be on the main bus. A 3-phase AC bus has 3 separate common lines, one for each phase. In plain English, when the engines are off and the aircraft is on the ground, the auxiliary power unit is started by the aircraft battery or an external power source. This unit powers the central electronic systems and allows pilots to perform pre-flight checks prior to engaging engines. Generally speaking, the APU is also used to power up the engines for starting. Following engine startup and acquiring adequate RPM, the APU can remain running, though it is typically shut down because at this point engines can sustain the power necessary to maintain electricity throughout the aircraft, utilizing the sequence discussed in prior slides. Should AC power be lost in flight, secondary and tertiary backup systems can be resourced to restore power to critical systems.